Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on complex integration, lecture number 12, in which I will prove the Morera's theorem. Also, I will show that why the converse of Cauchy-Goursat theorem does not exist. And only for this reason, this theorem is necessary. Before starting Morera's theorem, we need to state Cauchy-Goursat theorem. Cauchy-Goursat theorem is, let a function of z be analytic in a simply connected domain D and C be any closed continuous rectifiable curve in D, then integration along C function of z dz equal to 0. But the converse of this theorem does not exist. That is, if integration along C function of z dz equal to 0, then function of z need not be analytic. By assuming this result of Cauchy-Goursat theorem, we may not show that function of z is analytic always. By a particular example, I will try to show you that if integration of function of z along the closed curve C is 0, then it is not necessary that function of z is analytic. Example: let function of z equal to 1 by z square. Now we will try to find the integration of function of z along a closed circle C whose radius equal to rho. Let the equation of the circle be modulus of z equal to rho. Let this is number 1. This is number 2. Implies that z equal to rho e to the power I theta. Implies that dz equal to rho I e to the power I theta. Now, function of z dz integration along the circle C equal to function of z is 1 by z square dz along the circle C. This will be equal to 1 by z square, means rho square e to the power 2 I theta, and dz equal to rho I e to the power I theta d theta, and integration limit is 0 to 2 pi along the circle, and this will be equal to integration along the circle 0 to 2 pi. One row remains here, e to the power I theta I d theta. This equal to I by rho e to the power minus I theta integration limit 0 to 2 pi d theta implies that integration along the curve C, circle C, function of z dz equal to I by rho. Here integration is e to the power minus I theta by minus I limit 0 to 2 pi. I cancel, minus 1 by rho e to the power minus I theta limit 0 to 2 pi. This equal to minus 1 by rho e to the power minus 2 pi I minus e to the power 0. This equal to minus 1 by rho cos 2 pi minus I sin 2 pi minus 1 e to the power 0. This equal to minus 1 by rho, this is 1 minus I into 0 minus 1. This is minus 1 by rho, 1 cancel, 0, this is 0. Therefore, integration along the curve C, function of z dz equal to 0. This is number 3. But function of z equal to 1 by z square is not analytic. At z equal to 0, since our circle is center is origin, z equal to 0 and radius is rho. So at the center this function of z is not analytic. But from theory we see that integration of function of z along the curve circle C is 0. And here we see number 4 that function of z is not analytic at z equal to 0, means at the point inside the circle it is not analytic. So converse of Cauchy-Goursat theorem does not exist. So we have to think that what conditions are to be added with the Cauchy-Goursat theorem so that its converse may exist. Now we try to add the following concepts with Cauchy-Goursat theorem for the existence of converse of Cauchy-Goursat theorem. If however we assume that function of z is continuous within and on C and integration of function of z along C is 0, then function of z is analytic in C, that is converse of Cauchy-Goursat theorem is true. Now we state Morera's theorem. Let function of z be continuous in a simply connected domain D and let integration of function of z along the curve C equal to 0. where C is any rectifiable closed Jordan curve in D, then function of Z is analytic in D. Given that function of Z is continuous in a simply connected domain D, let this is simply connected domain D. At any point of this domain, function of Z is continuous, and also given that function of Z integration dz equal to 0 along the curve C, where C is any rectifiable closed Jordan curve in D. Let Z not be a fixed point and Z be a variable point. Let Z not be a fixed point and Z be a variable point in D. Let us join Z and Z naught by two curves. This is C1 and this is C2. Let C1 and C2 be any two continuous rectifiable curves in D, joining points Z0 to Z. Let C denote the closed rectifiable continuous curve consisting of the curve C1 and minus C2. If we start from Z0 along C1 and reach to Z, point Z, then from point Z to negative direction of C2 and reaches to Z0. This closed curve is denoted by C, curve C. Therefore, integration along the closed curve C, function of Z dz equal to integration along the curve C1, function of Z dz, plus along the curve minus C2, function of Z dz. Let this is number 1, implies that from 1 this is 0 equal to integration along the curve C1, function of Z dz. Here we may write this negative sign minus integration along C2 fz dz, implies that integration along the curve C1, function of Z dz equal to integration along curve C2, function of Z dz. Let this is number 2. Therefore, from 2 it is clear that integration of function of Z along any curve or line joining points z naught and z be same. Let capital Fz equal to integration limit z naught to z small f variable xi d xi. Let this is number 3. Therefore, capital F z plus h equal to integration limit z naught to z plus h f xi d xi. This is number 4. Implies that function of capital F z plus h minus fz equal to integration limit z naught to z plus h f xi d xi minus integration limit z naught to z f xi d xi, and this will be equal to integration limit z naught to z, we bifurcate this, f xi d xi plus integration limit z to z plus h f xi d xi minus integration limit z naught to z f xi d xi. Here this integration has been divided in two parts, limit from z naught to z, then z to z plus h. This and this cancels, only remains this part. Implies that f z plus h minus fz equal to integration limit z to z plus h small f xi d xi. Implies that capital F z plus h minus fz by h minus fz equal to 1 by h integration limit z to z plus h f xi d xi minus fz equal to 1 by h integration limit z to z plus h f xi d xi minus, we write here 1 by h fz multiply h cancel, remains same thing. This equal to, we take common here 1 by h integration limit z to z plus h f xi d xi minus, we may write this fz in place of h, we may write this integration limit z to z plus h d xi, because if we integrate d xi limit z to z plus h, we get xi. Here limit z to z plus h. This means z plus h minus z equal to h. So we may write this, bracket closed, this equal to 1 by h. Here we take integration z limit to z plus h, f xi minus f z d xi. Let this is number 5. Since given that the function f is continuous in D, therefore there exists epsilon greater than 0, delta greater than 0, modulus of xi minus z less than delta, implies that function of xi minus function of z modulus less than epsilon. Let this is number 6. Also, let modulus of h less than delta. It is obvious that the inequality 6 is satisfied for every point xi on the line segment joining z to z plus h. Taking modulus in both sides of 5, we get modulus of capital Fz plus h minus capital Fz by h minus small fz equal to modulus of 1 by h integration limit z to z plus h small f xi minus small f z d xi and modulus. This less than 1 by modulus of h integration limit z to z plus h modulus of f xi minus f z modulus of d xi. This is less than 1 by modulus of h integration limit z to z plus h, and this is less than epsilon from 6, epsilon d xi using 6. This equal to 1 by modulus of h multiply epsilon integration of this is modulus of h, and this is equal to epsilon. Therefore f z plus h minus f z by h minus f z modulus less than epsilon. taking limit h tends to 0, we get limit h tends to 0 f z plus h minus f z by h equal to small f z, implies that capital F derivative at the point z equal to fz. Let this is number 8. Hence, derivative of capital Fz exists and derivative of capital Fz equal to small fz. Since the inequality 6 holds for every point z belongs to domain D, implies that capital Fz possesses the derivative small fz at every point z belongs to D, means every point of the domain D, and consequently capital Fz is analytic in D. Since the definition of analytic is it is differentiable at every point, we know that derivative of an analytic function is analytic. Therefore, derivative of capital Fz is analytic, means small fz is analytic. Therefore, small fz is analytic in D, means every point in D. Therefore, our theorem is proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.